Alright, I was building this little transmitter, the amplifier part of this little microphone out of this old Forrest Mims cookbook. I'm sure, a lot of people have seen this circuit, light wave transmitter and receiver. I built the receiver. Let's see. I built the receiver, or the transmitter part of it, and again, it was a scaled down version of it. But this is a receiver actually. It's not the transmitter, but this is a receiver, and that's the output right there, and that's the power, and that's the ground. But it's actually really cool, what it does. It actually generates a pretty strong signal, and you can actually listen to your lights and everything with it. I actually had it hooked up to my little amplifier. I didn't make a video about it, but yeah, you can see the signal on the oscilloscope. It's a nice strong signal. I figured I could use it for a timing signal or something, but it's clipped, so you only see like half the signal, but it's nice and strong. It's really weird, how they did it. I might show you this a little bit later in the video. I'm not sure if I'm going to actually do this or not. I was just mostly kind of curious about whether I can get these stupid potentiometers to actually work in this board, because man, those things just do not want to stay down. You almost have to solder leads to them or something, and I don't know if I want to go through that pain in the ass factor. But still, that's why I decided to build this thing, just to test that, that potentiometer, because I already had the 741 sort of wired in for this project, but at any rate, turning our attention back to this project, this, is just always baffled me. Okay, these old books, always, use crystal mics, which are basically, almost impossible to come by these days, and so they, say, hey, for electorate, hey, you have this, it's a 3-wire mic, and that's just baffled me for years and years and years. Because I had these little microphones, so I was like, this must be something different, because they all have 2 terminals on them, But anyway, finally I got around to looking at a data sheet, because, microphones hadn't been that relevant to me all these years, but I know when I was a kid, and younger, in high school, this used to frustrate the piss out of me, because I just could never get anything with a microphone to work. But apparently there's a polarity to these things, and they're actually meant to be used this way. They actually have circuitry in it, but instead of having the 3rd wire like they apparently did back in the early 80s, well, they actually, you got to pull your own power supply off with like a 2K resistor or something like that. So this is still an electret microphone. It's just, it doesn't have 3 wires like it showed in this book. So I had to put, a 2.2K 2.2K resistor in there. Now I tested the amplifier. I've got it set, in fact, you can see what network analyses I ran on it, so you can see, it has a gain of about, 130 or so. So it's very narrow bandwidth, but it does have a gain of about 130 or so at maximum setting. And again, I was trying to do anything I could, so I did set the gain to maximum, to try to get it to work. But but that's good, because you can see it's generating a pretty weak signal compared to what I was generating. What I was generating, was actually putting out like 4.5 volts peak to peak or whatever. It was 4 volts or so. So for a 20 millivolt input, so that's what I was inputting into it, and I was getting a gain of 130 out of that. But you can see the signal, as we have it, it's averaging about little over half the range, because I got it powered by 9 volts. drawing like negligible current, but you know, as you can see, it's working. So let me snap my fingers there. So you know, but I mean, yeah, it is working now. So you know, that solves that mystery after all these years, because I've been confused about that for decades, and never really thought to take a look at the data sheet, because again, it always confused me, you know, for circuits like this, you know, because again, especially way back when, I didn't know much about analog electronics, not really, and you know, so it kind of confused me a little bit. But at any rate, you know, back when I was a kid in particular, then I just hadn't had need for it since, you know, I got older. Okay, you know, because I got out of electronics for a little while, and you know, was distracted, and you know, so got back into it in my early 20s. Let's see. But yeah, I was kind of wondering, you know, like I said, you know, a lot of these old books are based on crystal mics, so you know, even though I don't have any, because I did actually have one when in the early 80s, and that was the only one that actually did anything, but I broke it somehow, so you know, so yeah, since then I was microphoneless with projects like this, because books like this, you know, were my only reference back then, really. You know, it's way in the pre-internet days. But no, I thought, you know, since this thing is how I had it originally configured, you know, it's wired for ostensibly a crystal mic, you know, you fucking piece of shit. But at any rate, you know, I was wondering about taking, you know, one of these little piezo elements, because this is sort of like a crystal mic. I mean, in theory, you can use them as a crystal mic, even though it's a sound source. In fact, I really had to solder some wires onto this or something. If I have one, yeah, this will work. Okay, well, I'll try to put some clips on these pins here. Don't really want to stay on, but let's see if I can get some feedback out of it while I'm at it. Let's see. There. Testing. No, not really. I'm hearing hum out of it. Testing. Yeah, it's not really generating much sound. Oh, there it is. Generated a little bit. Hello? 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 Yeah, I can't really hear anything. Yeah, I mean, it should pick up on some kind of signal. I probably should take it out through a capacitor though. But at any rate, okay, so there's that, but let's see what happens if I remove my microphone and this and replace it with this. Yeah, it's definitely working. Here, show you the results. So yeah, I got, you know, my little you know, audio transducer plugged into it, and you can see that it's working. So this is making a crystal microphone, because I took that resistor out too, so so yeah, this makes an okay crystal microphone, one of these little piezo speakers. So that's what this is a little, you know, little kind of sound alert kind of thing, but it's broad frequency, so Hello! You can hear me speaking kind of right into it now. So yeah, it works. So, so that's an alternative, to a crystal mic if you don't have one. You can just kind of, if you got something like this lying around that you took out of some piece of equipment, as long as it doesn't have a built-in driver, you can kind of use it as a general purpose thing. You could probably even get them out of like old smoke detectors and stuff, because they typically have, piezo elements, but those, you can drive at different frequencies too, typically. So, so yeah, that's, that does the trick. Sitting here tapping on it. Yeah, it's pretty, it's actually more sensitive than that other one, technically. I'm getting a slightly bigger signal out. Well, I don't know. I mean, you still got to get pretty close to it before it starts, and speak into it before it starts, really picking up. So it's got some directionality to it. But I don't know. I guess it's a weaker signal than the last one. And remember, I got the gain turned up to maximum. So yeah, you got to get pretty close to it. I'm about 2 inches away from it right now. So, hello. So, you got to be louder, but I mean, it works. So, anyway, so there's that. And by the way, if you can, let's see if I can set the focus for this fucking thing. Shit. Hang on, this ain't gonna work. Okay. Yeah, I can't get this. Son of a bitch. I say, by the way, it's still really hard to see with the light and glare and everything. But, the way I told, because the terminal itself is not marked, so it does not have a plus marking on it. So, the way I determined it is I just looked at the terminals, and you can kind of tell that one is actually soldered to the case. So you should always assume that's ground when you see that, and one that's not. So that's the positive terminal, by the way. Yeah, but, I would say, that this microphone, it's going to take me a while to get the focus right on this, but I would say that, this microphone is better range, because I'm like, 12 inches away, and, you can see a stronger signal. When I get it up nice and close to it, you can see, it's probably a pretty strong signal. Really close to it and shouting, you get a huge signal. So, but again, it's got better long-range detection than the crystal. You got to get it pretty close to the crystal for it to really pick you up. And my understanding is that all crystal mics are kind of like that. They're pretty short-range microphones. So, I don't know, about the directionality of it, I can't make a good noise. But at any rate, yeah, it's definitely superior to the crystal mic I used, but still, in a pinch, that worked. So, yeah, and my design, again, I'm kind of disinclined, because the only pots I got a lot of are these little trimmer pots, like this. So, I bought a kit of them from Amazon, and, but yeah, my version of this circuit, that I was going to do, this little transmitter, I was considering trying it with a laser diode, to get longer range. But that would probably work well for digital communications, but I doubt that it would work all that well for, and plus I think those laser modules I have may not be just diodes. They may actually have built-in regulators in them. So unless it's digital information, you may not be able to use it for an application like that. But because lasers don't work like LEDs too. That's the other thing, is they have a certain minimal current that once you drop below it, they just basically stop, and they'll put out a really feeble light, and then all of a sudden, once you pass its threshold, then it'll kick on. But yeah, it's not really that suitable for analog signals. Is what I'm saying. Like an LED can actually respond to really feeble, weak currents and still put out plenty of light. Especially these days, the LEDs we have, the LEDs they had back in the frickin' 80s, boy, those are weak. Visible ones in particular. But the only LEDs that had any power to them at all were the infrared, and of course you can't see that. It's not so exciting. I'm still debating on whether I want to build this or not, because man, those potentiometers are a pain in the ass, and I do not want to have to solder leads to them. Man, that defeats the reason I bought them. I mean, I do have a fucking circuit board, that I made for this, but I really am disinclined to want to waste my inventory of components on something that I don't really need. So I don't know. I'm still trying to make up my mind whether I want to build at least this on a prototype, on a breadboard. But yeah, I've got this connected up to my little amplifier, so you can just hear it. I don't know, if I turned it up too loud. Hello? Testing. Yeah, I can't. Testing. I don't know, this thing probably. Yes. Not really generating much of a signal. Testing. Yeah, it's not generating a signal. There it goes. Damn. Fucking thing wasn't making good contact. Alright. Testing. Yeah. Testing. Yeah, I mean, I can hear my voice. You probably can't hear it because my microphone's away from the device, but yeah, I can definitely hear the echo. So, turn that down a little bit. Okay. But yeah, some tests here. Okay. I went ahead and basically just put an LED right across the output. Of the God, this fucking camera is just unfucking believable. Okay, I went ahead and put an LED, directly across the output, of the out of the op amp, so I'm not, going through the capacitor, and I got my probes connected directly across the output. So the yellow trace, is the output, just like before, of our microphone, and the blue trace is the output from my little audio pickup device, which I got, right here basically. So, you can see it. Let's see, how it's kind of wired up like a Christmas tree and everything, but again, that LED, was constantly biased, but that's okay. I got it set to where it's about 7 milliamps of a load. God, I hate this camera. I'm gonna have to get a different camera. But I got it set up, and here's my little detector, and again, you can see in the blue, as I bring it over to it, the blue is definitely picking up my audio, as I'm basically pointing it right at it. So, yeah, and you can, and I got the device hooked up to the audio amplifier, so and I can tell you, I can hear the voice, but now we're starting to get to the point to where it's causing feedback. through the whole system, because again, it's coming from our microphone on this thing, and yeah, when I got it pointed, basically right at it, um, it's picking up quite well. But yeah, I dispensed with the, I dispensed with, and like I said, this is a neat little module. You can, and again, you can hardly hear it, but you can listen to light um, with it. In fact, let me kind of show you what happens. Because here, this is like a 30 kilohertz signal, and you can actually see it and measure it on the scope. If I hook my little magnifying glass, which has a light in it, up to it at low range, you can hear the frequency coming from the light itself. So it's sort of like a scope probe in a way. But let me try to, I'll try to focus it at the analog discovery so you can see what it's doing up there. That's what the actual signal looks like. Let me see if I can lay this thing down for a minute to free up my hands. Okay, so you can see what the the signal actually looks like. Let me zoom in, and see. That's what I'm saying. It kind of clips it, but this has got a little PWM circuit obviously in it. But the frequency is about measuring. Let's see. Well, it's channel 1. Yeah, it's about 5 kilohertz on channel 2. So. And the more I aim it right at it, the larger the magnitude of the signal. So, God damn it. So yeah, like I said, you can kind of listen to light sources, and if I aim my lamp at it, you can see, you can see all the shit that's going on there. So that's the kind of signal that's coming out of the lamp. And again, this truncates it. So according to this, like a couple of 100 kilohertz that's coming out of this lamp right now. So if I pull it away, it's less prevalent, but yeah, I pointed at it. You get a nice strong signal. It's acting like it's not picking up a very good deal, because I think I had I turned my trigger off because I got sick of it stalling all the time. Let's make it channel 2. See if we can kind of stabilize it here. Yeah, so channel 2, yeah, it's about 34 kilohertz. Yeah, I was reading the wrong thing. But yeah, it's about 34 kilohertz. So, that's the frequency coming out of my, little desk lamp here. So, pointed right at that thing. And another set of tests I was running, too, on that circuit, to really kind of demonstrate the point, is I was taking a little LED like this, alright, which is actually a 12 volt LED. It came pre-wired, pre-ballasted that way. I was hooking up to analog discovery, its test clips, and using its wave generator to generate an output. It's got to be more than 20 millivolts, so there we go. It's starting to turn on. Okay, I got it up to full blast, 5 volts, but it's a 12 volt LED, so let me change the camera. Alright, so you can see my little detector sitting here, right? And that's the analog discovery signal coming through this LED, so which is going to be a pretty weak current, it, 15 kilohertz, it's really weird how it kind of interprets this. But yeah, you can kind of see the waveform over here. Man, I need to set that stand back up. Lower the frequency here. So it's like I said, son of a bitch. So you can see how it kind of clips it off. So, and that's owing to the really unusual design that this guy did. If you go look at this design, it's really strange. I mean, he's created basically a transimpedance amplifier here, but what's weird is it's a single supply circuit, right? But you can see he's got his positive terminal going to the negative supply rail, and then he's using the negative supply rail to, for his amplification. I'm surprised this does anything except to say, because, I mean, it can't reference lower. I mean, I'm surprised the input op amps will even do. The output is sure as hell not going to be able to go down below about 2 volts, and that's what you actually see there. You actually, you can, you can see the signal is at about at a 2 volt level, and again, that's as low as it's going to go. But yeah, it's just a really peculiar design, for them to, I'm just surprised it works, let alone, does anything. But I did try pulling that plus terminal up to a 50%, up to 4.5 volts, with a couple of, resistor voltage divider, and that really didn't do much good. It actually got worse, weaker amplification out of it. So, I mean, I'm still baffled as to what the actual theory of doing this is, particularly for like a 741, because they're not really supposed to be rail-to-rail op amps. And, like I said, even that Hazen book, I saw him do something similar by taking it to the positive, one of the terminals to the positive supply rail, and using the other one to try to find the balance point on that dual tracking power supply video that I did. That's what he was doing, and it's just weird shit. I haven't seen stuff like this really covered in any textbook or anything I've ever read, so I'm sort of baffled that this thing works at all. So it's just really, really quite curious. But it does work. That did give me the clue that well, shit, it seems like you could take an op amp, because like I said, an op amp doesn't know where ground is, period. You have to tell it where ground is, like with its terminals. And this makes me wonder if you can take an op amp, like on a 5 volt single supply rail to rail op amp, and feed it into like an Arduino ADC, as an amplifier, but just set its reference instead of it being, midway. If you're just trying to, make, do a DC signal, it seems like you can reference it to like ground or just about ground and only get a positive, arrange it so that you only get a positive swing, on a non-inverting amplifier, and that way, you get more range out of your ADC as opposed to having to interpret it from a midpoint like 2.5 volts or something, as its output. You could actually, tune it down to where it's like zero point 0.1 volts and then only have a positive swing on it. That seems plausible. I don't know how that would affect the gain stages and the output and everything, but that's an experiment, that would be interesting to run. But I don't have any op amps like that, so but it is kind of curious. This circuits like this make me wonder, especially if you had a proper rail-to-rail op amp, of which there are many out there. If you can find ones with decent frequency range for less than $3 or $4. But they are out there, and because most rail-to-rail op amps I've noticed have like a 7 kilohertz gain bandwidth product. I mean, it's pretty lousy. But it's fine if you're doing DC signal gain and so forth. But of course, the offset voltages weren't great on it. If you're doing DC work, that's something you got to pay attention to. I think they're like 15 millivolt offsets. That's like horrible. Of course, if they're single, I don't know if they had adjustment terminals, but it's usually going to be CMOS op amps that actually are rail to rail, according to some video I saw from TI. So, ostensibly JFET input op amps actually just can't go that far. So it's supposedly the CMOS op amps or the MOSFET op amps that actually can do that, both rail to rail input and output. But I don't know, it just makes you wonder. So I mean, because I've always just assumed, because you see it in textbooks all the time, that op amps generally should have an output, approximately midway, or definitely inputs that are based on midway. But then again, a lot of the applications you see are based on, AC signals, right? Having some kind of actual signal. But if you're just interested in DC, well, this could be a way of extending your range. That certainly warrants some research. Because again, I haven't seen this treated in any of the shit I've ever read. So, but you see circuits like this, and it makes you wonder, can these op amps, really perform well, or are they going to become really nonlinear if you do that? Because you're kind of pulling them closer to their, because their output, I don't think will have a problem with it, but doing that with the inputs might, because if you move your ground, instead of like on this circuit, the midway point would be 4.5 volts, and see right here you got a standard voltage divider, in that little circuit we built, so that's referenced to the midpoint, as its ground. But here, he's not doing that. He's actually pulling it to the negative supply rail, and my understanding is 741s aren't good at doing that. So it's just amazing how many times I've actually seen people do this, but it does make you wonder, I mean, why don't just set this arbitrarily, arbitrarily to any point you want, like closer to ground. And if you don't need that negative swing, and it's a pain in your ass, well, why not basically get it as close to the negative supply rail as possible? I would imagine that would work, and that certainly will warrant some investigation. Because again, that's not covered in any books I've ever read. So I don't know. Good luck finding that on the internet. I'm sure that's not going to be easy. What do you search for? You're going to come up with all kinds of garbage, especially with Google these days, being the piece of shit search engine it tends to be now. Like I said, 6 or 8 years ago, it was actually halfway decent, but man, it's just gone so far downhill. Even if you use quotes, most of the time it ignores those these days, it seems. Unless it's a part number or something, then it just tells you, oh, we can't find anything. If you put that in quotes, a lot of times, especially if it's something obscure you're looking for. But So at least it's honest with you there. Most of the other time, it ignores those fucking quotes. Um, oh man, I hate Google. Um, but at any rate, I was going to say too earlier that, when it came to, this LED, right? Okay, his circuit is based on, again, this is from like the 70s. I had this like the first electronics book I ever bought. I call it the Green Book from Radio Shack. So it's Forrest Mims, a fairly thick little book. But it had this circuit in it, and you can kind of tell it's a Forrest Mims kind of thing. But anyway, he has a transistor set up basically as a voltage follower, right? So he's not going to get any voltage gain out of it, but he'll get power gain, and that's because he's driving an infrared LED with it, with you know ostensibly, quite a bit of power. Let's see, those that have like a 1.4 volt drop across them, so 9. And again, it kind of depends on your bias point. And he's, setting, you can set your bias point with this, but, it could be as bad as 9 volts minus 1 point, I'll give it 1.5 for the, you know, VCE, and so divide that by 220 ohms. So it's maximum about 34 milliamps. This might put through there, which there are LEDs these days. On the take of it, the visible LEDs back then, boy, they were feeble. If you tried putting current like that for them, they burn right out. But some of the red LEDs can take current like that. If you've got good red LEDs anyway. But, I just said, well, LEDs are so fucking much brighter these days. They put so much current. That's why I used the green one. That's like one of the brighter LEDs. And I know this sensor will probably respond fairly well to that green color. So, I wanted to try to maximize the output. Red probably would have been better, but it's not going to be as bright. I mean, red LEDs in brightness have almost stood still for the last 22 years. And they've hardly gotten any brighter at all. Meanwhile, green and blue and white have all gone through the roof. So yeah, they're the definitely. It used to be red was always the brightest LED out there. I mean, for decades it was like that. But nowadays, no. I mean, the last 15, 20 years, yeah, that's inversed. I mean, green is really the brightest. Green or blue are the brightest. And even when you see a white LED, it's a phosphor that's actually converting like a green or blue dye to visible white light, so it's making a broad spectrum. That's what the phosphor basically does in there. Anyway, but yeah, I figured, I don't need these. I mean, why have this transistor? I got one already plugged into my breadboard. I was like, I don't really need that because I'm going to have to dig up the 50K potentiometer here because, you're going to need that to set the bias point properly for that 2N2222. But it's like, man, I'll bet you can get away just plugging it. I did hook it to this side of the capacitor at first, and it blinked occasionally, but, you got to kind of scream at it. And I was like, well, I'm just going to hook it direct, and, set it to low current, so, like I said, I stuck a 220 ohm resistor or something in there in series with it, because I knew this was going to be about midway on the output, in that neck of the woods. So, in fact, yeah, I can, you can see on the yellow probe right there, that's actually midway, where it's at right now. It's like a little over 4 volts on average. So, basically this is the signal the LED is seeing, that yellow trace. So, but yeah, I mean, it's just not necessary anymore with red LEDs. So, you can dispense with this and build your own, just get rid of all that, just hook your LED directly in with 220 ohm resistor, and, Bob's your uncle. In fact, you can try to make it higher than that. If you make it too much higher, you start overloading your op amp a little bit, although there's not going to be much of an ancillary load on it, with that 1 mega ohm impedance in it. Normally this is a no-no, but since he's using it as a you wouldn't want to normally use a 1 mega ohm resistor with some of these op amps because it creates too much noise, and and actually can cause them to get unstable if the impedance is too high. It's okay to do on like JFET op amps, anything that's really high impedance, but normally a bipolar op amp you wouldn't want to use more than 100K as any resistor element in it at all. But it's transimpedance, so he can kind of get away with it. It's kind of amplifying really feeble currents, and that's more or less what's going on here. So again, after you connect your 2.2K resistor to the output of the microphone and ignore this, then you'll get a signal out of the damn thing like we're getting now, and Bob's your uncle. So and like I said, other than that, you can generate your own cool signals out of, from Analog Discovery's little function generator, and you can put a square wave in it, triangle wave, ramp, alternate ramp, noise, pulse, trapezoid, back to our sine wave. So you can kind of see it's a sine wave. It's got still some lamplight being modulated on top of it. See, it's a clearer signal if I point that out of the way. It's picking up some of that, my mag lamp, some of its noise. Those little things are fucking noisy little lamps. I swear to God, they generate all kinds of electromagnetic interference and everything. Doubt that was FCC approved. So anyway, but yeah, you can see how it's just clipping half of it too. And again, when I moved it to the middle, I set the mid, I set my bias point in the middle by using a voltage divider, just like this transmitter did. If I use that on there, it just shifts the whole thing up. It's still, it's still clipped. So yeah, I couldn't get a, like a full sine wave out of it. And that's with it being, center biased, moving that, that positive terminal from the negative supply rail to the, 4.5 volts, just, it still clips it. So, I'm really not totally sure what's going on with that and why that's the case. But I mean, again, it's a transimpedance amplifier, which honestly aren't covered very well in books at all, to my disappointment, because they're really interesting amplifiers. It's just like this, for example, gives you a gain of 1 million. In fact, the transimpedance, it's easy to calculate because you just multiply it by that feedback resistor. Got my lamp focused, pointed at it again. That feedback resistor, whatever value that is, that's your gain. So because you're, amplifying current and turning it into a voltage. That's what a, transimpedance amplifier does. And they often call it trans resistance, but a lot of people, including Forrest Mims himself, refers to it as transimpedance. So that just sounds better than trans resistance. You have a transconductance resistor and everything else, but I mean, amplifier. But any rate, but that's that's kind of it in a nutshell. And I wanted to do one more test. I'm going to look into it. Alright, as a last little experiment, I wanted to do, taking a, basically a car stereo there, right? And I've got it hooked up to my oscilloscope over here because I don't want to hook something like that up to my Analog Discovery without evaluating it really thoroughly first. Okay, so that's, it's generating about 18 volts peak to peak according to my meter. So that's probably going to overheat my LED here, because I got an LED hooked to the speaker. I disconnected the 2 little speakers I have, but I got the volume turned up quite a bit. But it's going to sound like garbage, but doing with the waveform there. Um, the blue is, is the output. It's clipping quite a bit. But again, just hooking an LED to the speaker output. Oh boy. Produces, that kind of result. Let me see if I can just position the camera here. Try to turn the volume down a little bit. But like I said, this thing makes a lousy amplifier, given the fact it clips everything. But you can discern music at 100% volume. So yeah, it's putting out 18 to 22 volts. So even though I'm powering at 12 volts, it's drawing about half an amp. So anyway, hey, it's a neat little experiment anyway. So anyway, I think that'll pretty much wrap it up for this. So cheers. I just wanted to show you a couple of other things. Like for example, this is just a green LED, just like this one, and and you can use it. I have my probe set to 10x, and but you can use it. Let me turn off this other trace. Alright, the yellow signal is the LED, and I got it set to, like 50 millivolts per division. So, what you can see is I bring it close to, that LED there, that, see if I can get a, good view of it. So it's like I said, generates signal from that LED of over 100 millivolts. Let me switch it to, if I switch it to 1x mode, not quite as potent on the probe, so the higher impedance helps. You can detect this really good, like on a fluke DMM or something, if you're measuring the voltage across it, or particularly the current through it. It's good for detecting it. It's a really small amount, but it does respond. And I'll basically put my little flashlight on it. So and you can see when I do the flashlight thing, it detects the signal from my little mag lamp, just like the other thing did. But again, it's, pretty feeble, but it is, acting like a photodiode. So there is that. And here's the signal. I'll hold the Analog Discoveries LED out. So that's its signal, and of course it's acting like a rectifier, so you're only seeing part of it. Which there's a possibility that's why that photo detector was doing that too. It might have been sort of doing that, but still you'd expect that to actually have a bias current, because it does actually have a bias current into it, so you'd kind of expect it to be somewhere in the middle. Let's try one of those photo detectors and see how that responds, just like this. I'm sure it'll do the same thing though, because I don't have a bias current on it. Yeah, I don't think that'll show us anything particularly interesting. Let's see if I try it with one of the photo transistors, like what we're using on this board here, you don't get the same result. And the reason is because, I mean, you do get some kind of noise and shit, holding it in front of, let me try it with the LED here. But you do see some signal coming through, but it's extremely weak compared to that diode. And again, I hadn't changed the scope settings. So, let me try it with a little mag light. But yeah, it's not nearly as responsive, but then it surprised me because, see, an LED, when you use it as a photodiode, it'll actually generate a voltage. I mean, you can actually develop power from it. You do see a lot of Joule thieves and crap like that use LEDs as kind of a little solar cell, because they actually will generate a voltage, when you hit them with light. And that's why it works to put, an LED as a sensor here just hooked to my scope probes, because it does act like a voltage source. So whereas that transistor, not as much. It's doing a little something, but this transistor is not doing much. It's doing a little something, but not much. But okay, to kind of wrap this thing up, I did want to, I rigged, I took one of that green LED, and god damn it, I took that green LED, alright, to use as a photodiode there, and rigged up this amplifier so it's non-inverting. I hooked it up to my 3-output power supply to give us a proper low impedance ground reference. But anyway, I set the amplifier up to, be non-inverting, with basically right now I got it to approximately 10K for the feedback and for the, the reference resistor, on the inverting side. And I just have the LED, going from ground, alright, with that being its cathode on ground and anode going straight to the positive terminal. There's nothing else connected to the positive terminal. So, you can see what the results are. Let's see, we got, like minus 10 volts right now with no light attached to it. And as I bring my lamp over it, you can see it change. The voltage is going more and more positive, and then eventually we're pretty much into the reference territory. It's really quite directional, but you can see C2's voltage on maximum, so it's like 2.5 volts. I can wave my hands in front of it, and you can see it drop, and I can put my little LED flash portable magnifier over it, and we got that, and then I'll turn it up to full blast. Alright, and we're about 2.9 volts, just like you'd expect. Putting the mag light back over it, but I can increase the gain with my resistor box, so I can add like another 20K. Okay, now we're getting like 5.6 volts out of it, and I can take it up another 30K, and that's about the max. So so it acts like an okay amplifier if you use it if you use it just as a conventional voltage amplifier, because again, the LED is a voltage source, and I was getting at least 1 volt output on it when I tested the thing, all on its own, just hooking my probes across it. So that's probably the best way to do it. I was kind of farting around with the trans impedance thing a little bit, but with a single supply and everything, that was just making me pull my hair out. So I decided to switch over to this and try it this way first, and and it works quite well. I would have to go and actually see how much current these things generate to actually consider a actual transimpedance solution. But at any rate, it works as a detector in practice. Because see what happens, in the dark, that's why it goes, you know, swings to the negative power rail, because this positive terminal kind of doesn't know what to do with it. It kind of goes high impedance. So, if there's any offset voltage or anything like that, yeah, it's going to swing negative. And who knows what the LED itself is actually doing under these circumstances. I wouldn't expect it to be doing anything, um, but but anyway, that's kind of my theory of operation as far as what's going on. Why it keeps swinging negative in the absence of light, but then you get just enough light. Again, it starts going more and more positive as I bring my lamp closer, and because it's starting to generate voltage to counteract whatever offsets in there, and then once you got the lamp applied, okay, now we're up to full, and I can go ahead and reduce the gain back to how it originally was. So, but then you're seeing an actual full positive voltage that's offsetting, overcoming any kind of offset voltage and then some, unless there's some kind of negative current or something being generated here. I mean, I don't know, and I doubt that, but I haven't investigated it to that extent yet. I just wanted to establish using an LED as a photodiode, a legitimate way of measuring some kind of signal. Again, this would need some modification, preferably so it doesn't swing negative. You'd like it to swing to zero if there's zero input, although the negative thing does give you more range. Because like I said, that's over a 12 volt range. It does respond negatively, so who am I to say that's not potentially useful? Although it'd be nice to have it go the other way. I guess you could put it through an inverting amplifier and feed it into an Arduino or something with a voltage divider, and but of course it crosses the line when it goes when the light intensity gets high enough. But certainly it's in the negative territory. And again, light intensity is not that dark, over here. So, so it's just, I don't know, pretty interesting topic. I think more ought to be written on this subject, and there's scant information out there. I certainly found, some information on using LEDs. I mean, it's out there. It's just, the fuck is this? Oh, the microphone thing. Yeah, it's out there, but things like this, etc. There are some guides like this, and there are some other diode guides, but they usually don't specifically focus on LEDs. So it's as photodiodes, because they're not as sensitive as a photodiode is and everything, and they got slightly different properties. So I'm not sure that you can actually use them every way you can use a photodiode, because a lot of times photodiodes are actually used reverse bias, so especially with transimpedance amplifiers. So I don't know. I mean, it's warranted to investigate, because everybody has LEDs, right? So, and nice thing about LEDs is they do tend to be spectrally sensitive, to their emission color. Whereas photodiodes are broad range. I mean, I don't know if you know this or not, but I've got a whole bunch of like infrared diodes, and they actually respond pretty well to visible light. Even some of the really dark ones, you can actually get response, to visible wavelengths of light from it. I tried throwing my 3 different color lasers at it, at these, and it's amazing how much they do respond to like purple or violet and blue and red, and as well as just regular light. So at any rate, that definitely does it. Wrapping the video. Cheers.